Good afternoon, everyone. My name's Adam Leibovich. I am the Dean of the Dietrich School of Arts and Sciences and the College of General Studies. It is my distinct pleasure to welcome you all to this inaugural Pittsburgh Mathematical Horizons Lecture Series. This series was made possible by a generous gift from the Bentner Foundation. I'm confident Bill Bentner, who is a renowned mathematician in his own right, would be as excited as I am, and I'm sure all of you are, about our keynote speaker today. James Maynard is a professor of number theory in the Mathematical Institute in Oxford and a fellow of the Royal Society. His main research interest is in analytic number theory, particularly the distribution of prime numbers. It is for this work that he received the prestigious Fields Medal in 2022. So the Fields Medal has often been called the Nobel Prize of Mathematics, but that really sells it short because it's much harder to win a Fields Medal than it is the Nobel Prize. So for those of you who don't know, a Fields Medal is awarded only every 4 years, and you have to be under 40 to get it. So it's much more difficult, so it's much more prestigious. This award citation recognized James' spectacular contribution in analytic number theory, describing his work as highly ingenious, often leading to surprising breakthroughs on important problems that seem to be inaccessible by current techniques. In a recent interview, James described number theory as the study of whole numbers and how they interact with one another under addition and multiplication. He went on to explain his work as how these operations of addition and multiplication interact with one another, which turns out to be an exceptionally complicated and poorly understood mathematical phenomenon, even though they seem like the most basic mathematical objects. According to James, and I quote, "Primes are both important and also beautiful in their own right. They are the fundamental building blocks of nature and the universe," which, even as a physicist who would probably not use those fundamental building blocks of nature, I'd say they're primes, I still agree. Primes are beautiful, and they are definitely the fundamental building blocks. Just of math, not of everything. While his day-to-day research practice is surprisingly old school for a self-described millennial, a lot of time at his desk working with a pen and paper, James admits that much of his best work happens when he's not working at all. Quote, "There have been many days when I've worked very hard on a problem but made no progress during the day and got very frustrated. Then when I go on the walk home and trying not to think about maths at all, suddenly the solution becomes clear to me. A bizarre amount of progress has really been made on walks home, just wandering around, or in the shower in the mornings." James has said that it's a particularly exciting time for number theory, with many people making advancements in the field and lots of momentum to build on. "Most mathematicians are really motivated by mathematics." This is a quote again, sorry. "The thing that's always driven me is understanding truth in mathematics and getting to the heart of mathematical puzzles. The real satisfaction is from when I prove a theorem that I really like. I get this immense joy from that. That's what drives me on. That's what drove me initially, and that hasn't changed at all." So we're looking forward to hearing more from Professor James Maynard shortly. Before he gets to take the actual stage, I'd like to welcome Carl Wang Erickson, Assistant Professor in the Department of Mathematics here in the Dietrich School, whose expertise is also in number theory, which makes him the perfect choice to serve as today's moderator. So, Carl.
All right, thank you, Dean Leibovich, for being here. It's such a pleasure to see you all. I do see some people standing in the back, so if you see a chair more central than you that you are comfortable to squeeze into, please shift a bit, and then we can make some more room at the ends. But in any case, welcome everyone. It's on behalf of the Department of Mathematics. It's really wonderful to see you all here. And without further ado, I'm really pleased to introduce James Maynard to give our inaugural Horizons Public Lecture.
Okay, hi everyone. So I want to thank the organizers for inviting me to give this inaugural Horizons public lecture. And I really want to thank all of you guys for coming today and taking time out of your day to listen to me speak about the things that really matter to me in my research and my mathematics. So as you heard, most of my research is on prime numbers. And that's what I want to share with you today. So the fundamental question and aim of this talk is for me to try and give you a reasonable insight into why I like prime numbers so much and why I think they're both so important but also so fascinating and worth devoting one's life to studying. So the fundamental question here is, why should anyone care about primes? And maybe we've already touched on this a couple of times from quotes that you've heard of me beforehand and what I've just said. There's this somewhat magical tension with prime numbers, that on the one hand, they seem to be, to mathematicians, these absolutely fundamental basic building blocks that are some of the simplest objects that we can possibly study. And it's maybe one of the first things that you will study when you try and really delve into mathematics as a pure mathematical subject. But at the same time, despite being these fundamental, basic, simple building blocks, they remain remarkably poorly understood. So the study of prime numbers goes all the way back to the ancient Greeks, and mathematicians have really studied prime numbers for hundreds and thousands of years, but many of the basic questions to do with prime numbers still remain unsolved even today. So lots of the simple questions, some of the first questions you might ask as a mathematician trying to understand prime numbers, we still don't know how to answer, despite some of the best mathematicians in history having worked on these precise problems. And it's this tension between them being these fundamental, simple building blocks, but still poorly understood, that really drives me on and makes me find prime numbers just the most fascinating objects to study. And so I'd like to try and give you an insight into these two different sides of prime numbers. And therefore, the schedule of this talk is I want to first of all talk about how prime numbers really are these building blocks and why this makes them so fundamental. And then I want to demonstrate this central aspect of prime numbers by a couple of examples. One example of applications to the real world that I hope will matter to you, even if you couldn't care about pure mathematics at all, and another example completely in the opposite direction, which is right at the heart of pure mathematics. And then I want to finish by hopefully having convinced you that primes are these important but mysterious objects, sharing with you some recent progress that means that even though we've been stuck studying prime numbers for hundreds or maybe thousands of years, mathematicians nevertheless can make some progress, and we are slowly edging towards some of these big motivating conjectures that have dominated the study of prime numbers. So let's start off with primes as building blocks, which is why primes are really important to mathematicians. So just to make sure that we're all on the same page, we better check that we know what prime numbers are. So a prime number is a whole number which is bigger than 1 that cannot be written as two smaller whole numbers multiplied together. So for example, 15 is not a prime number because it can be written as two smaller whole numbers multiplied together. It's 3 times 5 or 5 times 3. Whereas 7 is a prime number. You can't write it as two smaller numbers multiplied together other than 7 times 1. And 7's not smaller than 7. So maybe this is a mathematical definition of what a prime number is, but I think if you see this for the first time, the natural question is, why on earth should you care about this? This seems like some weird mathematical curiosity, and maybe it's something that, geeky people like to go off and play with in a room, but it doesn't feel like it's an important thing at all. So why on earth should this be an important definition, and why should this make prime numbers an interesting object to study? Well, there's this fundamental principle that works across the whole of science, that the world is full of these very big, complicated objects. And they're often too complicated to study at once, but a very powerful way of trying to get some handle on these complicated objects is to break it down into much simpler building blocks. Maybe oversimplifying somewhat, if you're a chemist, you can understand certain properties of large molecules by understanding the constituent atoms that make up the molecule and how they're joined together. And it's exactly the same thing for mathematicians, and if you're a number theorist, you want to understand the whole numbers and properties to do with the whole numbers. And it turns out that from a mathematical point of view, there's lots of properties of the whole numbers that are complicated, and so to me, whole numbers are these big, complicated objects that we don't really understand at all, but you can start to get a handle on how whole numbers interact with one another if you can break them down into simpler building blocks. And because there's this fancy theorem called the fundamental theorem of arithmetic that says that every whole number can be written essentially uniquely as prime numbers multiplied together. The only different ways you can have it is by changing the ordering. So 15 is 5 times 3, or it's 3 times 5, but you can't have any other numbers other than 3 and 5, which is prime factors. This means that lots of questions to do with whole numbers can be broken down into questions about the constituent building blocks, which are the prime numbers. And often, when you break it down into a question about prime numbers, it becomes a more tractable problem. So there are problems to do with whole numbers that at first sight we don't know how to solve, but you can break it down into the constituent building blocks of whole numbers, which are these prime numbers, to turn it into a simpler question about prime numbers, and then solve that problem about prime numbers to solve the whole problem about primes. So to me, this is supposed to be demonstrating how I might think about whole numbers that are 135, can be written uniquely as a product of prime numbers, and its prime factors are 5 and then 3 copies of 3. And so in some ways, this is like 135 being some molecule made up of 1 5 and 3 3s. And understanding this prime factorization allows us to break complicated questions to do these whole numbers down into these simpler problems. But as I mentioned at the beginning, the problem is that even some of the most basic questions about prime numbers have resisted the attempts of mathematicians to solve them for hundreds of years. So even if in principle you have a simpler problem, sometimes we often get stuck as soon as we're trying to study the prime numbers. So I've got a couple of quotes that I'd like to share that from different mathematicians trying to kind of explicate this point a little bit more. So one is by Don Zagier, a famous mathematician based in Bonn in Germany. And he says, despite their simple definition and role as the building blocks of the natural numbers, the prime numbers grow like weeds amongst the natural numbers, seeming to obey no other law other than that of chance, and nobody can predict where the next one will sprout. And to demonstrate this difficulty, maybe one of the most natural questions that mathematicians might ask if they're trying to understand the prime numbers is how frequently do prime numbers occur? And another way of phrasing this is if you give me some number x, the challenge is for me to tell you how many primes there are less than x without just going through and calculating each one by one by hand. And it turns out that this sort of most basic of problems, we have what we believe is a fairly precise answer to what it should be, but that turns out to be one of the most, and often dubbed the most important open problem in mathematics, known as the Riemann hypothesis. So the Riemann hypothesis is somewhat technical to state precisely, but it's essentially a precise answer to how many primes are there less than some given number. And even if you don't care about the distribution of primes, one other incentive is that there's a $1 million reward if you prove the Riemann hypothesis. So even just answering this most basic question about how many primes are there, we already run into essentially the most famous and sometimes called the hardest problem in mathematics, and there's already a $1 million bounty if you solve it as an extra incentive. And one quote that I really like from David Hilbert, who was one of the best mathematicians of the 20th century: "If I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven?" So somehow, even if we're just looking at the most basic question you can possibly ask about the distribution of primes, quite quickly we run into some of the most famous and most intimidating problems in the whole of mathematics, but also some of the most important problems. Okay, so I've said that primes are important because we can take whole numbers and break them down into questions about prime numbers, which are maybe simpler, and I'd like to try and demonstrate this to you through giving two examples. So the first example is going to be a real-world example. It's every day nowadays we're buying things online, and if I want to buy something on Amazon, maybe a new math textbook for me, because that's the sort of thing that I like, I want to be able to tell the Amazon servers what my credit card details are so they can charge me and they can send me the math textbook. And to do this, my credit card number is a number, but I don't want to just broadcast this to Amazon, because then any other person, potentially a nefarious person, could take my credit card details and then use them to buy whatever things that they wanted as well. So to get around this problem, we encrypt the credit card numbers, and so there's a process of turning my credit card number into a secret code, so even if someone can find out what the secret code is, they can't get back to what my credit card number is. And it turns out that the computer algorithms that encrypt these things work on lots of the basic properties of whole numbers, adding and multiplying numbers together. And so that means the whole process of encrypting, and therefore decrypting, is all a process about manipulating whole numbers together, using addition and multiplication. In particular, many of the most popular cryptographic systems that are used in day-to-day purchases online rely on these computer algorithms that are all about manipulating whole numbers. And because it's a question to do with whole numbers and multiplying numbers together, you might hope that you can analyze this situation through the lens of prime numbers and trying to break it down into a question about prime numbers. And it turns out that for many of the most popular cryptographic systems that are most commonly used today, that's indeed the case. And there's a few different ways it can happen, but at least in one of the most common ones, it turns out that if you want to hack someone else's credit card details, then essentially you can do this if you can turn a large number into its prime factors. So we've seen that 15 is 5 times 3. Using this cryptographic system, if I had chosen 15, then you would be able to hack my credit card details if you could work out that 15 can be written as 5 times 3. Now, for 15, that's quite easy. Here's another example, 449,623. So that's maybe a little bit harder, but I guess everyone in the audience notices that that's obviously 521 times 863. But if you don't have small numbers like 449,000, we believe this becomes really very, very difficult, even if you have very powerful supercomputers. So for example, take this slightly larger number, which is the sort of size of numbers that are maybe used day to day when you're making credit card purchases. This was, in fact, a open challenge problem, and there was a $75,000 reward that was offered if you could turn this number into its prime factors. And you're allowed to use whatever computer resources you like, but the point is, we think as soon as you get to these very big numbers, it's actually exceptionally difficult to turn a number back into its prime factors. And this is And principles like this are what many of the most important cryptographic systems that secure the internet today really rely on, that doing this sort of process is hard. And so here we've seen that we have a computer algorithm that I imagine all of us use very, very regularly. It's absolutely vital for the modern world and digital security. And because it involves whole numbers being multiplied together in certain different ways, it can be analyzed as properties of prime numbers. But this question of factorization, we maybe think it's hard in general, but you can also analyze it even further using prime numbers. And it's a fact, due to a mathematician named Pollard, that if, maybe I'm lying slightly, but yeah, if the large number has a prime factor p, such that p minus 1, when you take 1 away from one of those prime factors, that itself has lots of small prime factors, then there's a trick you can do, which means that actually it becomes very easy to factor the number. And so it would be very easy to hack someone's credit card details if they had one of these prime factors where when you take away 1, that number itself only has small prime factors. So this is analyzing one step further, and to get around this possible issue, when people were choosing numbers to use to encode and encrypt credit card details, one suggestion that people used that's not so popular these days was to try and avoid this Pollard possible attack as strongly as possible, and so choose primes, only use prime factors p, where p minus 1 is very far away from having lots of small prime factors. So if I have a large prime, it can't be a multiple of 2, so it has to be odd. So when I take 1 away from it, it has to be a multiple of 2. But maybe the furthest away it can be from having lots of small prime factors would be having this necessary factor of 2, and then the remaining factors just being one big prime factor. That's about as far away you can get us from having lots of little prime factors. And so these were called safe primes. Primes p, such that when you took away 1, you were left with 2 times another prime number. And this was to try and be safe from the point of view of cryptographic secure systems. But then a natural question arises if you're thinking about doing something like this. Well, how often does this occur? That it would be a pretty bad cryptographic algorithm if before you could purchase anything on Amazon, you needed to find a prime p where p minus 1 divided by 2 was a prime number, and this never ever occurred. The algorithm would just stop and you wouldn't be able to do anything. But it would maybe be even worse if there was a precise list of 1,000 primes when this did occur, because your algorithm would choose one of those 1,000 primes, but any hacker could also just look up this list of 1,000 primes, and then they could easily factor your number and hack all your credit card details. But it turns out this question about how many primes p are there with p minus 1 divided by 2 a prime number is an unsolved problem in pure mathematics to do with the patterns in primes, and this predates the internet or anything like it. In fact, this question has been open for over 100 years, and we don't know how to solve it. So quite quickly, in this example, we started off with internet security and whole numbers being multiplied together. Because it was whole numbers being multiplied together, we could start to analyze it using prime numbers. We found that there were that hacking your credit card details turned into being this question about turning a number back into its prime factorization. We thought that was hard in general, but then we saw that you could analyze it a bit more and use properties of prime numbers to say that it's easy in some cases. So then maybe we try and get around it by avoiding these sorts of obstructions, but then we run into 100-year-old open problems in mathematics that have got nothing to do with the internet. It's purely a question about prime numbers and patterns of prime numbers that just exists in pure mathematics. Okay, so that's one example in the real world for making internet purchases. I now want to shift gears almost entirely and move completely to the realm of very pure mathematics. And maybe the most famous equation in the whole of pure mathematics is Fermat's last theorem. So this is the claim that there are no solutions in whole numbers to a to the power n plus b to the power n equals c to the power n, where a, b, c, and n are all whole numbers, and n is bigger than 2, apart from the obvious ones where one of a, b, or c is equal to 0. So this was famously posed by Fermat and then solved by Andrew Wiles just around the turn of the century. And this is maybe one of the most famous results in the whole of pure mathematics, and it's an absolute, it's a hugely celebrated proof that uses a huge amount of the modern machinery of pure mathematics. But nevertheless, it's a question that involves whole numbers multiplied together. And so given that it's involving whole numbers multiplied together, you can think about trying to break it down into a question about prime numbers. And this is essentially the first step in Andrew Wiles' proof. And it's a fact that rather than considering all integers, all whole numbers n, it's enough to only consider whole numbers n when n is a prime number. And in fact, you can show that essentially just by recalling a little bit of high school arithmetic. So imagine that Fermat's last theorem was false when n is 15. So that means there would be some whole numbers a, b, and c such that a to the power 15 plus b to the power 15 would equal c to the power 15. Well, if you remember from high school, a to the power 15 is a to the power 5 to the power 3, because when you take one power and then you multiply it, you multiply the exponents. So this means that if a to the 15 plus b to the 15 is equal to c to the 15, then a to the 5 cubed plus b to the 5 cubed would equal c to the 5 cubed. And so that means that a to the 5, b to the 5, and c to the 5 would be a counterexample to Fermat's last theorem when n equals 3. And then if you think about what we've done here, this means that if I have a counterexample to Fermat's last theorem for some exponent n, then I automatically get a counterexample to Fermat's last theorem for any prime factor of n. And so if Fermat's, and then if you say the same thing sort of in the opposite direction, the contrapositive is the fancy name for it, that means that if Fermat's last theorem is true for every n which is a prime number, then there are no counterexamples whenever n is a prime number, and this argument shows that you can't have any counterexamples for any multiple of any prime number, which is all numbers. And so Fermat's last theorem must be true itself. Now, for those of you who are particularly eagle-eyed, you'll know that there's a slight flaw in this argument because you have to be careful about the case when the exponent is 2, because there are solutions to a squared plus b squared equals c squared. That's Pythagoras' theorem, another very famous result in mathematics, but it was known to Fermat already that there were no solutions when n is equal to 4, and using the fact that there are no solutions for n equals 4, this means that you really do only need to consider Fermat's last theorem with n being a prime number. Okay, so this is essentially the first step in Andrew Wiles' proof of Fermat's last theorem. Unfortunately, there's not quite enough space on the slide for me to give a full proof. But again, we've seen that this reduces some problem about whole numbers down to a problem to do with prime numbers. And it turns out in this case, this is a useful reduction, and it does make the problem technically simpler. But even before Andrew Wiles' groundbreaking work, you can nevertheless still analyze Fermat's last theorem a little bit more, and you can think about it from the perspective of prime numbers. And way before Andrew Wiles, one of the people who made really dramatic progress on Fermat's last theorem was a mathematician named Sophie Germain. And she proved that if p is a prime number such that 2p plus 1 is also a prime number, so if there's this strange property, then there's no solutions to a to the power p plus b to the power p equals c to the power p, with the slight caveat that at least or they have to be a multiple of P. And so this was called the first case of Fermat's last theorem. And mathematicians at the time believed that, first of all, you would solve the first case of Fermat's last theorem, and then by some technical extension, you'd solve the second case. So this meant that she solved the first case of Fermat's last theorem for any exponent P when 2P plus 1 is also a prime number. And this predated Andrew Wiles's work by well over 100 years. And this was the first sort of really fundamental theoretical advances for Fermat's last theorem in general. But if you see Sophie Germain's theorem, this holds only for primes P where 2P plus 1 is also a prime number. And so a natural question is, well, how often does this occur? This is not maybe a great theorem if it never occurs at all. She hasn't really proven anything at all then. So the question then becomes, how often does Sophie Germain's theorem work? So how many primes are there such that 2P plus 1 is a prime number? But now if we think a little bit, we realize that this is precisely the same problem that I said in the previous example about the real-world cryptographic systems, about how many primes P are there such that P minus 1 divided by 2 is also a prime number. And so we've seen that there are these two examples to do with multiplying whole numbers together, both of which doesn't have prime numbers in the statement of the problem at all, both of which, because they involve whole numbers multiplied together, can be analyzed through the spectrum of prime numbers. And by thinking about it a little bit, you quite naturally start running into problems about the patterns in the primes. And both of these turn out to be exactly the same theoretical problem in pure mathematics about patterns in prime numbers, and we don't know how to solve this problem. This is an open problem that's been open for over 100 years. We do know how to solve Fermat's last theorem, but we still don't know this question about, are there infinitely many Sophie Germain primes? And so this sort of picture occurs in all kinds of problems, and it motivates mathematicians like me to try and develop a general toolbox for trying to understand the distribution of prime numbers and questions like this, patterns in the primes of how often do you have a prime P such that 2P plus 1 is also a prime number. And one of the most basic questions that you can study in on the distribution of primes is a big global question about how many primes are there less than some number x. And we saw that that was some formulation of, like, very closely connected to a formulation of the Riemann hypothesis. The Riemann hypothesis was essentially a strong answer to this large-scale question about the distribution of primes. But you can also ask small-scale questions about the distribution of primes. If you're interested in the sequence, you tend to ask large-scale questions and small-scale questions, and the natural small-scale questions are to do with maybe the gaps in the sequence. So let's try and think about gaps between prime numbers. So one of the most celebrated results in prime number theory, and one of the most famous theorems in the whole of mathematics, is the prime number theorem, which is a weak version of the Riemann hypothesis in many ways. And this says the number of primes up to x is roughly x divided by the logarithm of x. And another way of thinking about this is that if I'm looking at primes of size roughly x, then the typical gap between prime numbers of size about x is about log x. So the logarithm function is a function that gets bigger and bigger as you go further and further down the number line, which means that as you go further and further down the number line, the primes gradually get sparser and sparser and sparser. And so the average gap between prime numbers gets bigger and bigger and bigger. But just because the average gap gets bigger and bigger and bigger, it doesn't necessarily mean that all prime gaps get bigger and bigger and bigger. And it could be the case that occasionally you get primes that are unusually close together. And so a natural question is, are prime gaps always this big? So if you look at square numbers, for example, it is the case that the gaps get bigger and bigger and bigger. Or is it the case that, unlike the squares, primes sometimes come nestled up close to one another? And we can start to just think through this and maybe do some experiments on a computer. So maybe the first thing, so prime numbers are whole numbers, and so any difference between prime numbers certainly has to be a whole number. So the first thing to do is to try and classify all gaps of size exactly 1. And this is quite easy, because if you take two consecutive whole numbers, one of them has to be even, and there's only one even prime number, which is 2, and so 2 and 3 are the only pair of primes that differ by exactly 1. So we've classified all prime gaps of size 1. The natural thing to now do is to classify prime gaps of size 2. But if you start looking for these, it turns out that you start finding quite a lot on a computer. So 3 and 5, 5 and 7, 11 and 13. The first pair bigger than 1,000 is 1,031, 1,033. The first pair bigger than 1,000,000 is 1,037, 1,039. The first pair bigger than 1 billion is 1,007, 1,009. And these pairs of primes that differ by exactly 2 seem to keep on coming and coming. So even though we expect the typical gap to get bigger and bigger and bigger, occasionally we still find, and actually we find quite a lot of them, these primes that come nestled up very close together and differ by exactly 2. And so another very famous conjecture in mathematics is that there are infinitely many primes that differ by exactly 2. And this is another one of these very famous problems in maths that's been open for over 100 years, and we don't know how to solve it. Lots of the finest minds have worked on the twin prime conjecture, which is this conjecture, but it's still very much open. So it's another question about patterns in primes, and almost the most basic question you could ask about the patterns in primes, we're stuck on. And you don't need to stop there. You can think about general gaps. What happens not just for primes that differ by 2. Okay, we're stuck on that. Maybe you could think about primes that differ by 3. Well, if two whole numbers differ by 3, then one of them has to be even. So again, there's only one possible gap where primes differ. There's only one possible pair of primes that differ by exactly 3 when one of the primes would be 2. In this case, there's 2 and 5, but they're not consecutive, so there's no gaps of size 3. But then if you look at, and that's true for any odd difference, one of the two numbers is always going to be even, so you can only possibly occur when the smaller prime is equal to 2. But just like we found with 2, if you look for prime gaps of size 4, we find there's lots and lots and lots and lots of them. If you look for prime gaps of size 6, we find there's lots and lots and lots of them. If you look for prime gaps of size 8, we think there's lots and lots and lots of them. So there's nothing terribly special about 2 in the twin prime conjecture, other than it's the smallest whole number which is even. We believe that for any even number, there should be infinitely many pairs of primes that differ by that number. And similarly, you can start trying to look for more general patterns of triples of primes that come nestled close together. And there's some more complicated obstructions now. So, for example, if you're looking for there being 3 primes in an interval of length 5, then it turns out that there's only 4 possibilities, 2, 3, 5, 2, 3, 7, 2, 5, 7, and 3, 5, 7, because if you're bigger than 2, then all the 3 numbers would have to be odd numbers, and then the only way they could be contained in an interval of length 5 is if they're of the form n, n plus 2, and n plus 4. But it turns out that for any whole number n, one of n, n plus 2, and n plus 4 must be a multiple of 3. If n's 1 more than a multiple of 3, then n plus 2 is a multiple of 3. If n's 2 more than a multiple of 3, then n plus 4 is a multiple of 3. And so this means that if you have a triple of primes containing an interval of length 5, you must contain either a 2 or a 3. And so that's the complete classification of triples containing an interval of length 5. But if we look for triples containing an interval of length 6, then suddenly we find there's lots and lots and lots of these. Maybe 6 should be 7 here, because I guess we want even numbers. We're looking at primes of the form n, n plus 2, and n plus 6, or n, n plus 4, and n plus 6. So yeah, maybe that 6 should be a 7. Okay, so we've seen now that prime numbers are these building blocks of whole numbers, and there's a few different questions that we've seen. One coming from very modern world, day-to-day things to do with internet cryptography that we all rely on regardless of whether we care about prime numbers or not, and one to do with the opposite extreme, pure mathematics, and in both cases you can analyze it because it involves whole numbers multiplied together, and you can try and get an understanding of this to do with prime numbers. And in both of those cases, it quite quickly started leading to questions about patterns in prime numbers that have been studied for hundreds of years, and we don't know how to solve the answer, not through lack of effort. And so then, maybe in the aim of developing a general toolbox, mathematicians would like to come up with ways of answering very basic questions about patterns in prime numbers, such as how many primes are there less than x? Are there infinitely many pairs of primes that differ by exactly 2? But we've seen that these basic questions, either on the large-scale distribution of primes or the small-scale distribution of primes, run into some of the most famous problems in the whole of mathematics. We're running into the Riemann hypothesis and the twin prime conjecture. And so it would be not unreasonable for someone in your position to say that mathematicians are pretty useless at studying prime numbers, that maybe I've convinced you that primes in principle are these building blocks of arithmetic, and maybe I've convinced you that there's lots of cases where you can take problems to do with whole numbers multiplied together and reduce it down to a question about prime numbers, but it just seems a bit hopeless that we just keep on running into all these problems that are these very famous problems that some of the world's best mathematicians in history have really tried hard to study, and we don't know how to solve any of these problems. And so that's a bit depressing. So to move on a slightly more positive note, I want to finally try and convince you that despite the fact that many of the really basic and fundamental questions about the distribution of prime numbers remain unsolved, and despite the fact they've been worked on for hundreds and hundreds of years, it's actually a very active and alive area, and we are making incremental progress on these fundamental conjectures. So, yeah, just to recap, we've already seen in today's talk many different questions about primes and many natural questions that arise in the things that we've looked at, starting off with problems that had nothing to do with prime numbers whatsoever, which are related to patterns in prime numbers that's completely theoretical mathematics. So how many primes are there, how many primes p are there with p minus 1 divided by 2 as a prime number? That was the question that we arrived at when we were analyzing the possibility of using safe primes in cryptographic algorithms, and when we were asking how often Sophie Germain's theorem on Fermat's last theorem held. Related to the cryptographic side of things, a natural question is, we saw that there was this problem when you had primes p where p minus 1 had only small prime factors. But this wouldn't be much of a problem if this basically never occurred, but it might be a big problem if it occurred all the time. So a natural question is, how many primes p are there where p minus 1 only has very small prime factors? We've seen that if you want to look at the small-scale distribution of primes, such as the gaps between prime numbers, then maybe the most basic question here is the twin prime conjecture, which is how close can primes be to each other, and are there infinitely many pairs of primes that differ by exactly 2? We believe the answer is yes. In fact, we believe that there's infinitely many primes p, that p minus 1 divided by 2 is a prime number. We believe that there's infinitely many pairs of primes that differ by exactly 2, and we believe that there's a pretty precise answer for how many primes p are there where p minus 1 only has very small prime factors. And finally, there's maybe the most famous question of all, the Riemann hypothesis that I mentioned right at the beginning, about how many primes are there which are less than x. And the Riemann hypothesis would give us a very precise conjectural answer as to what these things are. So in all of these cases, we have problems that have been studied for over 100 years. They're all sorts of fundamental questions on the distribution of primes, and we're stuck on all of them. But in each case, we believe quite strongly, and we have very good guesses as to what the answer should be, This fits with all the kind of computer numerics you can run as well as you could possibly hope. And for virtually all of these problems, there's actually been exciting progress over the past decade or two. So, for example, I don't know how to prove the twin prime conjecture. I would love to prove the twin prime conjecture, and I can't prove that there's infinitely many primes that differ by at most 2, but I can prove with collaborators that there's infinitely many primes p that differ by, there's infinitely many pairs of primes which differ by at most 246. So 246 is quite a lot bigger than 2, but if you remember, the typical gap between primes gets bigger and bigger and bigger without any bound at all. And so when you're looking at big enough primes, the typical gap between primes is bigger than a billion, 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 and nevertheless we're saying that there's these pairs of primes that differ by at most 246. And until relatively recently, there was no such finite bound known, and so this was really kind of important progress towards and in the direction of the twin prime conjecture on small gaps between primes. Similarly, we've seen this question about Sophie-Germain primes, about are there infinitely many primes p such that p minus 1 divided by 2 is a prime number, and how often do they occur? And this is relevant to internet cryptography and things like that. And I don't know how to solve this question about Sophie-Germain primes, but I can show that there exist some fixed numbers a1 and a2, which are not necessarily 1 and 2, but that's what I like to show. But there are some numbers a1 and a2, such that there's infinitely many primes p with p minus a1 divided by a2, a prime number. So this is like a weak version of Sophie-Germain's question. And again, up until a couple of decades ago, no such result of the existence of any pair of numbers a1 and a2 was known. Similarly, we talked about other small-scale questions about prime numbers, such as clumps of many primes occurring together, and we were talking about clusters of 3 primes being in intervals of length 6, and it gets a little bit more technical to state, but in the same way that we can prove a weak version of the twin prime conjecture, we can prove that there's infinitely many clusters of triples or quadruples or however many primes you like, that occur unusually closely together. So in an interval of a bounded length. And the size of the interval that is needed to contain 10 primes is rather bigger than what we expect the truth to be, but nevertheless it's some finite number in the same way that 246 is rather bigger than 2. But for pure mathematicians, this is a big advance because it's some finite number. And even if you're maybe not too worried about the theoretical side of things, but having an existential panic that next time you buy something on Amazon, your credit card details are going to get hacked, well, all of these theoretical results are very much in keeping with the heuristics behind all of these algorithms. So even though I can't prove that it's difficult to turn a number into its prime factors, and even though I can't prove there's an abundant supply of safe primes, we quite strongly believe that both of these things are true. The fact that whether these things are true or not is absolutely vital for internet security, but this provides some theoretical justification for the heuristics that underlie the assumptions behind these algorithms that we rely on day to day. Finally, maybe just to finish up now, the last problem that I mentioned was the Riemann hypothesis. And so I don't know how to prove the Riemann hypothesis, but just this summer, I've been involved in work with collaborators that's making progress on questions very closely connected to the Riemann hypothesis. So again, the precise statements of this are slightly difficult to state, but it's saying that even if the Riemann hypothesis is false, it can't be false in a terribly bad way, that there are somehow few counterexamples to the Riemann hypothesis. And so the point is that on all of these different questions, we started off with problems to do with whole numbers multiplied together. Because prime numbers are the building blocks of whole numbers, we were able to reduce it down to questions to do with prime numbers. We quite quickly started encountering very natural questions to do with the patterns of primes. But unfortunately, these patterns of primes questions are famous unsolved problems. But just over the past decade or two, mathematicians have made lots of theoretical advances and continue to do so on these famous old 100-year-old problems. And so slowly but surely, we're inching towards resolving some of these questions, like the twin prime conjecture and like the Riemann hypothesis. So as a final recap, there are many important, interesting questions which to do with whole numbers, and in particular, whole numbers being multiplied together. And when they involve whole numbers being multiplied together, often, not always, but often, you can reduce it down to a simpler problem involving prime numbers. So we saw this when we were thinking about internet cryptography, and we saw this when we were thinking about Fermat's last theorem, and it happens in lots of other cases as well. And if we had a very general toolbox for understanding the distribution of primes and patterns in prime numbers, then we would often be able to solve these problems, and we would be able to either solve or make very strong progress towards answering the original question to do with whole numbers, that at first sight had nothing to do with primes whatsoever. Unfortunately, many of these basic questions to do with the distribution of primes are famous unsolved problems that have resisted the best efforts of the best mathematicians for centuries. But nevertheless, we're slowly but surely making progress, and it's actually a very, very exciting time in prime number theory because there feels like there's lots of different advances and a new young generation of mathematicians who are really doing things that seemed completely impossible just a decade or two earlier. So thank you very much for listening. I hope you've enjoyed the talk.
All right, thank you, James, so very much for the very interesting lecture about the mysteries of prime numbers. This is a time where we can have some questions, and there's some stands set up on either side. So if you can make your way, if you have a question, to one of those microphones, please go ahead. And I might be able to, if you're very much in the center, I might be able to pass one to you as well if those don't get too busy. All right, so please go ahead.
What is your Erdős number?
My Erdős number, okay. So I think it's 2 that I haven't co-authored with Paul Erdős. Unfortunately, he died before I really was a professional mathematician, but I have co-authored with Carl Pomerantz, who certainly co-authored with Paul Erdős. There's probably some other people who have Erdős number 1 that I've co-authored with, so Erdős number 2.
Thank you.
Thank you. Yeah, so please come down to the microphones if you're interested in asking a question. Yes, please.
Hi. So I have what I'm sure is a very basic and naive question, but I'll ask it anyway. So when you talk about primes as building blocks, you talk about, you formulate this in terms of multiplication, right? So we can multiply them together to get other whole numbers, and they themselves are interesting because they are not the multiples of any other numbers. But of course, they are the addition of other numbers. So my question is, why is multiplication the sort of central concept for characterizing other numbers rather than addition?
Okay, yeah, that's a good question. And in some ways, it's not multiplication or addition, but it's the combination of the two. And if you have a purely additive problem, then in some ways you might, all the whole numbers under addition are generated just by the single number 1. And so sometimes the analogs of the additive analogs of some of these questions, rather than being boiled down to a question about prime numbers, if it's purely additive, you might think the analogous thing would be boiled down to a question about the number 1, which is often totally trivial. So if you're thinking about gaps between whole numbers, that's totally trivial because every whole number just has a gap of size 1 because it's a very additive question. And actually, there's quite often similarities when you have purely multiplicative questions, that it does boil down to a question about prime numbers then, but often it's something that's almost a trivial question about prime numbers. And the real subtleties with the whole numbers and the real thing that characterizes whole numbers from my point of view is the interplay between addition and multiplication. So in all of the famous questions I put up on the board, it didn't just involve primes, it involved primes with a little bit of addition. There was p minus 1 divided by 2, or it was 2 primes that differ in an additive sense by exactly 2, so primes of the form p plus 2. And what's really kind of under the surface there is that it's primes which are multiplication and addition involving the additive generator 1. And so it's the interplay with multiplication and addition that I think is the sort of fundamental thing that characterizes the whole numbers.
Thank you.
All right, next question, please.
Given the pace at which number theory is evolving and new advancements are being made every day, so I have 2 questions here. First, do you think that in your lifetime the Riemann hypothesis will be proven or disproven? And secondly, how will the quantum computing and artificial intelligence change this field of number theory and prime number theory?
Okay, yeah, good question. So I'm totally a believer of the Riemann hypothesis, so I'm completely convinced that the Riemann hypothesis will not be disproven in my lifetime, because I think it will never be disproven. So that's the easy bit. In terms of when the Riemann hypothesis will be proven, I get asked questions like this quite often, and it's always a bit of a fool's game. Somehow with the Riemann hypothesis, it really feels that we don't have the right way of thinking about it, and we don't have the right mathematical tools to really get a hold on the proper conjecture itself. We can make some partial progress by saying it's it's not wrong in a bad way, but making real progress and getting to the heart of the matter, I think we currently don't have the right tools, so it seems very, very open to me, and so I have no idea if it'll be proven in my lifetime. But I remember when Andrew Wiles was asked one of these problem questions, he said that if you're randomly distributed in time, then on average, you'll be roughly at the midpoint of how long a question's been open for. And so maybe you should therefore guess, if you have no further insights, that a problem would be open for as long as it has been open. Which in the case of the Riemann hypothesis is, so Riemann made his predictions in 1859, I think. So 180 years. So unfortunately, I don't think I'm going to live 180 years. Then the other question was about quantum computing and AI. So I think AI will change the way that mathematicians do mathematics quite dramatically over the next 10 to 20 years. And I think they'll be hugely useful as a sort of mathematical assistant that can take on lots of the burden of mathematics. But I personally am a little bit skeptical as to the extent to which AI is going to take over mathematics and take over the creative process of research mathematics. But I'm very optimistic that it will actually allow us to refocus very much, and the job of a pure mathematician researcher will be much more focused on the big creative ideas and less some of the tedious things that the AI can take care of. So I think it will have dramatic effects on the practice of mathematics, but I don't think it's going to replace us as mathematicians. Maybe I would say that because I'm a mathematician. Quantum computing would have very significant implications for internet cryptography, that it would make turning a number into its prime factors very simple if you had a real quantum computer. You have to be a little bit careful because there's lots of different potential competing definitions of quantum computers, and most of the prototype quantum-esque computers that we have at the moment are very far from the types of things that might be factoring numbers. But so far, I'm not aware of quantum computers having much further impact on pure mathematics. That you can theoretically imagine what sort of computations become feasible with a perfect quantum computer, and even if those were available, it speeds up a few select things very dramatically, but those aren't the things that I feel are currently limiting us in our day-to-day mathematics. So I think it would have big implications for some of the things I've talked about, like cryptography, but maybe not so much in the day-to-day process of a research mathematician.
Thank you.
Just so you know, I'm going to take only a few more minutes of questions. We do have a reception afterwards, and we'll be able to speak with James more then. But I'll take 2 or 3 more. All right, next, please.
Yeah. So one is when you are showing this p minus a1 by a2. So I just realized that, you are telling that these are fixed numbers. So how are they fixed? Because I just realized that if I take 17 and take a1 and a2 just 2 and 3, and then this a1 and, I can get prime numbers for both if the a1 and a2 are interchangeable. So like if a1 is 2 or a2, a1 is 2 and a2 is 3, and if I interchange, both will give me the prime number. So how much they are, how you are fixing this a1, a2, and if there are special constant on that. And another question is like, why prime numbers appear? Is that some hidden theory which is actually out of that, prime numbers is appearing? Like why prime numbers occur in the nature?
Okay, yeah, so for the first question, maybe I wasn't very clear on my slide. The theorem proves the existence of fixed numbers a1 and a2, but it doesn't tell you exactly which numbers they are. In the same way that primes that differ by at most 246 means that there's infinitely many pairs of primes that differ by some even number, which is between 2 and 246, but it doesn't tell you which one it is, and we expect it to be all true for any of those. And similarly, so for the A1s and A2 pairs, an important part of the theorem is it's merely proven the existence of these fixed constants rather than you being able to choose specific choices like 2 and 3. In terms of why prime numbers appear, so I assume you're sort of alluding to the fact that prime numbers and prime-related objects appear in various situations in nature, for example. And again, this is often believed to be prime numbers naturally arise out of kind of biological processes and things, often because they're the things that sort of self-correlate the least part, because different prime numbers are multiplicatively independent of one another. That if I have a population of rabbits that hibernate, I think it's cicadas where there's this famous example, and it's been hypothesized that if they hibernated for 6 years and predators lived on a 3-year cycle, then they would be naturally in sync with one another because 3 divides 6. And so to make it maximally difficult to avoid a predator being in sync with your cycle, you want to hibernate for a prime number of years. I think there's some questions as to whether this is really a valid explanation or not, and there's some debate in the sort of mathematical biological world about whether this is a convincing argument or not, but it's properties like that which I think arise that because prime numbers are sort of multiplicatively independent, because they're the building blocks, that's how, even through a completely natural biological process, sometimes they can arise.
Okay. Yeah, thank you.
I think we have one more question here. Sorry, for the rest of you.
I was going to say, is like the twin prime conjecture like fundamentally like unprovable because you can't find all the prime numbers within 1 to infinity, so you can't like find all the ones that fit a certain criteria.
So I strongly believe that the twin prime conjecture is provable, and the Riemann hypothesis is provable, and all the questions I put here are provable in principle by humans using standard mathematics. And there are results that are known to be sort of independent of the axioms of mathematics and genuinely unprovable, but they tend to have a rather different flavor, and so I would be completely shocked if any of these questions are genuinely unprovable. I think there's lots of similar questions that we genuinely can prove, and so I think they are provable. The fact that it's dealing with infinitely many prime numbers means that it's a difficult problem, but not, I think, an impossible problem at all.
All right. Well, I have a few people to thank before we finish. So we very much want to thank mathematics department staff that made this possible, the technical staff here. Thank you, Dean Leibovich, for coming in the introduction, and a special thanks to Professor Armin Shakura and Ivan Yotov that worked on making this happen with me. Also, thanks to the Benter Foundation for the generous funding. And finally, let's thank James Maynard again.